Okay, last page here in the note handouts is just a couple of extra practice problems. So a pretty diverse set of information here in this particular chapter. So I always feel like it's useful to go back and just revisit that calculation with the molarity that we need. And I just have a few more examples here of calculating oxidation number, oxidation state for components in the equations. Now, this is hardly a comprehensive practice. You want to do your precipitation reactions, your molecular equation, net ionic equation, total ionic equation. You want to work on your acid reactions, acid with metal, acid with carbonate, or acid with base, and be able to predict the products and balance those equations as well. But the example here kind of brings into play some of these issues. We've got 49.8 milliliters of 0.150 molar calcium hydroxide, and we want to figure out how many milliliters of 0.350 molar sodium carbonate would be required to completely react with the calcium hydroxide. So that's a stoichiometry question, and that means we should have a balanced equation. Now, we don't have a balanced equation, but that's okay because we've learned how to balance equations, and this is a reaction we should be able to identify the products of, which would help us balance the equation. So sodium carbonate, right, obviously is a carbonate, but we're not so worried about the carbonate here as we are the fact that it is reacting with another soluble compound that is not an acid, and that means this is more likely a potential precipitation reaction. Now, carbonate is soluble with sodium, but it won't be soluble with the calcium. Now, we don't need the total ionic equation here or the net ionic equation, so we can kind of do those in our head. We can get the molecular equation, then we can balance it. That'll help us solve this problem. So calcium carbonate is going to be our product. Calcium's +2, carbonate's -2, so that'll just be CaCO3. That'll actually be a solid here. 2 sodiums here, there's 2 hydroxides there. Those would be spectator ions in this case because sodium salts are always soluble. Sodium hydroxide will also be soluble here as a product. Now, because there's 2 sodiums and 2 hydroxides, there would be a 2 right here. Now, what that means is the ratio of the reactants, which is what we have up here, the 2 reactants, is 1:1. So that's necessary for us to do our calculation, but 1:1 is not going to be anything that's going to change our math as we work through that calculation. Okay, now we know how much calcium hydroxide we have. That would be a good place to start. 49.8 milliliters of the calcium hydroxide solution. Right? And if we want to use that equation, we need to get to moles first because the equation is describing the mole ratios of the participants there. So the calcium hydroxide solution is 0.150 molar. That means that's how many moles there are in a liter of that solution. So 0.150 moles of calcium hydroxide is going to go on top here. 1 liter would go on the bottom, but I'm going to change that to 1,000 milliliters of that solution so I can cancel directly with the milliliters we started with. Again, if you're not real comfortable with that sort of trick, you can look at that and do it in an extra step, milliliters to liters, then use the molarity there for that one. Okay, now we're in moles. Now we can use our equation. Now, after balancing our equation, we know 1 mole of calcium hydroxide is going to react with 1 mole of sodium carbonate in this reaction. Right? And then moles of sodium carbonate, we want to figure out volume here. How many milliliters of sodium carbonate? So since that's aqueous in our solution, we need to use the concentration there. Now, in this case, I want the moles of sodium carbonate on the bottom, so I'm going to invert the molarity, and I'm going to put 0.035 moles of sodium carbonate on the bottom of my fraction there because that's what I'm canceling out. And 1 liter of the solution would be what goes on top. Remember, moles per liter here is what's really hidden by that capital M. I'm going to change that to 1,000 milliliters. Right? 1 liter equals 1,000 milliliters of sodium carbonate solution. Again, just to save that step of writing out liters to milliliters again. And again, if you're not real comfortable with that step yet, do it as a separate step. But right, we're going to see that again and again and again now that we're dealing with solutions. Okay, that's the units we're looking for, milliliters of sodium carbonate. And now we can solve this problem. So 49.8 times 0.15 divided by 1,000, well, times 1,000. I should have looked at that ahead of time. We didn't need to put both of those in, divided by 0.35. Okay, that comes out to be, it looks like 3 significant figures for the problem, 21.3 milliliters. So yeah, what I was saying is we divide by 1,000 here, we multiply by 1,000 there. Those could cancel out as well, right? But it doesn't change anything if you do punch them both in. Just make sure you don't punch one in and not the other. Okay, so it take 21.3 milliliters of sodium carbonate in order to figure out, in order to have enough to precipitate all of the calcium hydroxide solution or react with the calcium hydroxide solution. Okay, the last little set here is oxidation number. So for each of these, right, there are atoms that are pretty easy to figure out around the outside, right? Maybe, well, we should probably do both in this case, right? The central atom here is really the one that would be the one you'd have to figure out by using that 7th step, which is the algebraic sum. So if you want to pause and try those out real quick, I'll go through them fairly quickly and then we can see what the answers are. But maybe you want to pause and try these out. Okay, oxygen's -2, there's 4, that's -8. Potassium is +1, so that means bromine here has to be +7. Right, so let me write that in. Get the algebraic sum there. The bromine would have to be +7. So bromine's oxidation number here, or oxidation state, is +7. 4 oxygens, each is -2, that'd be -8. Each potassium is +1, there's 2 of them, that's +2. So that means the manganese here would have to be +6 in terms of its oxidation state. 2 hydrogens here, each hydrogen gets to be +1, that's a total of +2, but there's a minus on this entire thing, that means the nitrogen is -3. Iodate, oxygen's -2, there's 3 of them, that's -6. Total charge on the ion is -1, so the iodine here would have to be +5. This is perchloric acid, although just like it would be the same in perchlorate, the anion form. -2 for oxygen, 4 oxygens is -8, +1 for hydrogen, only 1 is +1. That means the chlorine here in perchloric acid, or also in perchlorate ion, is +7. H2ASO3, again -2 for oxygen, 3 of them, that's -6. +1 for hydrogen, 2 of them, that's +2. This is an ion with a charge of -1, so that means the arsenic here would have to be +3. So 2 + 3 - 6 would equal -1. Now, this one is kind of mixed. It's an ionic compound, so manganese we would get from knowing what the charge on this polyatomic ion is. Chlorate's chlorate's -1. There's 2 of them, that's -2, so this is manganese +2. Right? Now the chlorine in the chlorate would be another thing we'd need to think about. So pull out that ion, ClO3 minus, again -2 for oxygen, that's a total of -6. So the chlorine here is +5 in the chlorate ions. And notice +5 in chlorate, it's +5 in iodate. There are similarities there across those formulas. Okay, that wraps up chapter 4. Lots of things to think about in chapter 4, things you definitely want to practice, and a few things that you just really have I don't like the term memorize, but you've got to know. You have to know when an acid and a carbonate react, what the products are. You have to know what ions are likely to be soluble, which ones are likely to be insoluble to balance out those reactions. And you have to know how to use molarity when it comes to calculations.